All right, let's talk about something that can feel, well, just a little bit overwhelming. Complex electrical circuits. You know the ones, right? All those loops and sources and resistors. It's a lot. But today, we're going to learn this absolutely brilliant technique to cut right through that chaos. So yeah, let's dive in.
Okay, just take a look at this thing. Seriously, it's a total maze, isn't it? You've got voltage sources, current sources, resistors all over the place. Honestly, this is the kind of problem that makes you just want to, I don't know, close the textbook and walk away. But what if I told you there's a much simpler way to look at this? So, here's the deal. All we really want to do is find the current flowing through one specific part of this whole mess, that load resistor, RL. But here's the real headache. What happens if we want to swap that resistor out for a different one? Say, a bigger one or a smaller one? Does that mean we have to redo all that complicated math from scratch every single time? Ah, no way. There has to be a better way, right? And you know what? There is. This is where our secret weapon comes in, Thevenin's theorem. Now, this thing is brilliant. It basically says that any two-terminal linear circuit, and really linear just means it's built from predictable stuff like resistors, can be replaced by something ridiculously simple. We're talking a single voltage source in series with a single resistor. That's it. The whole complicated thing boils down to just two components. And this right here, this just perfectly shows the magic of what we're talking about. We take that entire confusing black box of a circuit on the left, and from the perspective of our load, we replace it with that simple, predictable source on the right. I mean, how cool is that? It's just such an elegant solution to a really messy problem. Okay, so how do we actually do this? We're going to break it down into two simple missions. Mission number one, find the Thevenin voltage, which we call VThev. This is also known as the open circuit voltage. So to find VThev, the very first thing we do is we just take out the component we care about. In this case, our load resistor, RL. We just pluck it right out of the circuit. And that leaves us with two open terminals, which is exactly what we need. All right, so here's what our circuit looks like now. See? RL is gone, leaving those two terminals, A and B, just hanging open. And our entire mission right now is just to figure out the voltage between those 2 points. Okay, so after we run some standard circuit analysis, the usual stuff, we're not going to get bogged down in the nitty-gritty of that right now, we find that the voltage across these open terminals is 30 volts. Exactly. And just like that, boom, we've found our Thevenin voltage. VT is 30 volts. Mission 1, complete. Nice. All right, we've got our Thevenin voltage locked in. So it's time for mission 2, finding the Thevenin resistance, or RTh. Now, this is sometimes called the look-back resistance, and you're about to see exactly why. Okay, to find Rthen, we got to do something kind of interesting. We need to turn off or deactivate all the independent power sources in the circuit. And here's how that works. Any voltage sources, we replace them with just a plain wire. That's a short circuit. And any current sources, we just remove them, leaving a gap. That's an open circuit. So this is what's left after we've zeroed out those sources. Now we stand at terminals A and B, and we look back into the circuit to figure out the total equivalent resistance from that specific point of view. See why they call it look-back resistance now? So the calculation here is pretty straightforward. It just involves combining the resistors that are in parallel and in series. And when the dust settles, the result is a nice, simple 4 ohms. And that, my friends, is our Thevenin resistance, R through. So mission 2 is officially complete. We now have both pieces of our simplified puzzle. We did it! We found our two key values, a VThev of 30 volts and an Rth of 4 ohms. And now comes the best part, the payoff. Let's put this all together and see our beautiful, simple solution in action. And here it is. Look at that. All of that crazy complexity from our original circuit, it's just gone, replaced by this wonderfully simple equivalent circuit, a 30-volt source in series with a 4-ohm resistor. And the amazing thing is, this little circuit will behave exactly like the original, big, complicated one, at least as far as our load resistor is concerned. But the real beauty here, the real power, is how incredibly easy this thing is to use. You want to calculate the current through any load resistor we attach? It's now as simple as using good old Ohm's law. It's just so fast and efficient. It's almost cheating. Don't believe me? Let's prove it. Let's go back to our original problem. What's the current if that load resistor, RL, is 6 ohms? Let's find out right now. The answer? 3 amps. Done. That's it. No more pages of algebra, no more complex analysis, just one quick, simple calculation. But this is where it really shines. What if the design changes? What if we need to swap that out and use a 36 ohm resistor instead? What now? No problem at all. Another quick calculation, and the current is 0.75 amps. See? We can now analyze any changes to that load almost instantly. It's all thanks to our Thevenin equivalent circuit. It's a total game changer. So the big takeaway here is this. The Thevenin's theorem isn't just some clever math trick for a test. It's a genuinely powerful way to think, a tool for managing complexity. It's about replacing an overwhelming, messy problem with a simple, functional equivalent that gets you the answers you need fast. And that kind of leaves us with a final thought, doesn't it? We use this powerful idea to simplify an electrical circuit, but where else could this mindset apply? I mean, what other complex problems in your life or in the world could be solved if we just found their simple, elegant equivalent? Something to think about. Thanks for joining me.